Hello everyone, my name is Konrad. I work here at Software Mansion. I maintain TypeGPU, which you can see now on the screen, which is a library to help you develop cool things on the web and maybe React Native using TypeScript instead of writing shaders. I have the chat from YouTube in front of me, so if you're on YouTube, feel free to ask questions. I will try to answer them. But if you are on X, unfortunately, I don't see the chat, so you will have to come over if you want to ask some questions. Yeah, so let's get started. What are we going to do today? As advertised, we're going to be implementing liquid glass effect using shaders written in TypeScript on the web. Yeah, so let's go over our plan. So what is the end goal? Let's draw a nice rectangle. We'll be creating a canvas, loading an image on it, and using shaders. Of course, the image itself also we will do everything in shaders today. And we will create the nice liquid glass effect. So we'll have like we'll have a rounded rectangle that will curve around the edges. You know how liquid glass looks. We'll do it in steps. So I will do a short introduction along the way to what even shaders are. So if you have no idea what I'm talking about, what is a shader, we'll get to that. And also how to contribute an example to TypeGPU. So I will not be using like a custom setup. I will be forking and cloning the existing repo we have and adding an example like you can do also after the stream. If you want to contribute an example, we are always open to checking it out. If you have any questions regarding what I'm explaining, I will be happy to answer it on stream. If you decide to follow along and try to code with me, feel free to do so. It will be pretty fast, so if you have some debugging to do, unfortunately, I won't be able to help you, but after the stream, feel free to write to me or hit up on our Discord server, which you can see on our homepage. We try to be active, and if you need any help, we'll see you there. So let's start by exploring the repository. This is TypeGPU on GitHub. I could just clone it here since I'm maintainer, but I will fork it, so it's easier for you to follow along. We'll be fine with just the main branch. OK, so let's clone the repo. The font in the terminal is pretty slow, pretty small for you, I think, but we'll not be spending much time here, so don't worry about it. OK, I will be coding in Z. This is my editor of choice for today, but feel free to use any you like. So let's explore the repository structure. TypeGPU is a monorepo. That means we have all our documentation and the library code and all the helper libraries in here. So there's the packages directory where TypeGPU and all of the helpers live. We will not be spending much time here today. We'll be using it, but not exploring how the code actually works under the hood. Maybe another time. What we'll be interested in is the apps directory where we can see TypeGPU docs. TypeGPU docs is basically what you see when you enter the main page. Could you make the camera a bit smaller and anchor to the bottom right? No, the camera will have to stay here, but if something is occluded, I will just disappear and reappear when I think it's fit. That I don't think there was anything important up until now. So when I looked over something and you didn't see something, just tell me and I will go back and show it again. So this is the homepage, which also lives in TypeGPU docs. We'll be most interested in interactive examples, which is the page when you can look over examples the team made and we can look at the code, play with it. There are also a lot of parameters you can explore. And this is what we're going to base our example on. You could also just download the latest version of TypeGPU and the plugin and do it yourself in your own HTML's TypeScript code. But it's easier for us to just focus on how TypeGPU works. Okay, I will just grab it over here. So if we look at the source and we are interested in examples, these are the same examples we see here. We can see that, for example, the simplest of examples is triangle, where the structure is as follows. We have an index HTML file, which is the actual HTML we will use. We have the index TS, where the code lives. So this is where we spend most of our time today. And we have meta.json, which just helps us parse the examples we have in the repository and display them properly. So we'll be basing our today's code on probably just the triangle. Also, we also have thumbnails, but they are not necessary if you're just playing around with it. Okay, first things first, let's install everything we need. So we'll do pnpm install, just pnpm. Okay, and if you want to look at the scripts we have in our repository, we are most interested in the dev script. So we'll do pnpm run dev. Okay, so now we should have our own TypeGPU up and running. Let's take a look. Yeah, it works. Great. So we basically have the same, but any changes we make will be reflected here in real time. So let's get started. And I will start explaining everything about shaders once we start coding, so I can just put it into code very fast for you. Let's create our new folder where our example will live. We'll do my liquid glass. Okay, so we have to follow the structure. So we'll just copy over the HTML since it's just a single canvas. That's all we're gonna need today. Everything will be done via shaders, so we don't have to worry about any HTML and CSS. And next, let's do index TS. And I will copy over the meta file and just change the title to liquid glass. And also remove the tag since it's not what we are going to do today. Okay, let's check it out. So index is empty. Let's check if it's all updated live. So we do yep. Okay, we have an empty example. Yes, then let's get to coding. So what we are going to do today, as I showed you, is basically this. We're going to render a picture. We're going to use some fancy assigned distance fields to render a shape. And using this shape, we're going to offset the picture to make it look just like the liquid glass effect, or more or less like the liquid glass effect. We'll start with loading the picture. So, of course, loading a picture and displaying it on the screen is not something particularly difficult. Let's just do it on the standard, like you probably know, the 2D context, very simple. So let's get started with that as a sanity check that actually our code does something. So let's fetch the canvas. Oh, where's my intelligence? Oh, I'm in the wrong, oops. Okay, let's do the canvas. Document query selector canvas. Okay, and it of course returns HTML canvas or null. We don't have to worry about null since it's just an example, so we'll just assert it. And we'll get our 2D context for now. So context, get context. Of course, what we are most interested in today is the WebGPU context, but let's start small. So we also have to assert that it's there, so we don't have to null check it. Okay. Oh, I missed that. Okay. I happen to know that in our public directory we have already an image, so we don't have to worry about finding and downloading one. We'll just use this one. It's pretty simple. So this is the standard web way, nothing revolutionary yet. So we just do response. TypeGPU. And then file name is plums.jpg. Okay, this is of course asynchronous, so we'll await it. Okay. And also we'll import a TGPU from TypeGPU, of course, okay? To just make our dev server know that awaiting top level is fine. We'll, of course, use TypeGPU later, but for now, let's do the simplest thing possible and just display it. So const blob will just take the raw data, so we can do await since asynchronous response.blob. This is just the standard web way of loading the image, and we have the excellent image data, excellent create image bitmap API, so we don't have to worry about parsing the file actually. And the format, okay, so we are left with the promise of image bitmap, so of course the further await. Here it is. Okay, so now all we have to do in the 2D context is image data, the context, draw image, yep, with the image data, and we'll have to set the offset. For us it's 0, 0. Okay, we can now check if anything is wrong. Oh, we couldn't decode it. Oh, I misspelled the file name. Okay, yeah, cool. As we can see, it's a little. As we can see, the image itself is smaller than the canvas, so we only loaded it partially. If the image was bigger, I believe it would be a runtime error. So, but we're just checking that the environment is good. We are moving away from the 2D context right now. So, let's go over some shader fundamentals, shall we? Okay. So what is a shader? A shader is basically a program we tell the GPU to perform. The GPU is massively parallel, so it's a different execution model to simplify it. So we can, yeah, what's a shader? Of course, just as I'm explaining. So we are doing, oh, that threw me off, I'm sorry. A shader is a GPU program, so a program basically that's on the GPU that runs in parallel. So if we do, for example, you can think of it as a for loop, but each iteration happens roughly at the same time. Let's say that's enough of a definition for now. And to create a shader program in WebGPU, we're going to need two specific shaders, which one is a vertex shader and the second one is a fragment shader. I'm going to go over what does that exactly mean. Okay. So a vertex shader, basically the job of a vertex shader in this basic form is to output a list of positions. I'm going to be supplementing and using WebGPU specification, also along with WebGPU shading language, which is Wixel specification. These are the pages you are most welcome to go and use as reference. They are pretty good once you get to know them. So we can take a look at how coordinates work. If we go over here, this is what it's called the normalized device coordinates. So everything in shaders will happen in this space. So we won't have positions that are like 2 or 8. We have everything is normalized between -1 and 1 when it comes to the shader space. And basically the job of a vertex shader is to output vertices but in the basic form, like a list of triangles. So let's go over it. So for example, we output this point, the second point, which would draw a line, and then we can specify a third point, which in combination will form a triangle. So the job of a vertex shader is to output this position that I'm pointing my cursor to, then the second one, and then the third one. And every 3 vertices will form a triangle. So for every outputted triangle from a vertex shader, a fragment shader will be run. A fragment shader job is to go over the area of the triangle, and for each pixel that falls within the area is to run some code. This can be like arbitrary code. It can do pretty much anything you want. For this simple use case, we'll just be outputting like a static color, or maybe as the end goal, we'll be outputting some the picture we loaded with some offsets. But we won't be drawing triangles today because our job is to output an image and then do some transformations on it. So basically what we want is to run the fragment shader on the entire screen. So we can run the program for each pixel and at each pixel decide what are we trying to do. The simplest way to do that would be to draw just 2 triangles. So we are going to draw a triangle like this, going from here to here, here to here. Of course, I'm leaving some space. There will be no space left. We'll be covering the entire canvas. So this is one triangle. And maybe let's start with that. So our goal is to have a vertex shader that has some coordinates, and it outputs it in a particular order. So we'll output this one, then we'll output this vertex, and then we'll output this vertex. When we hook up a fragment shader to it, for each little point that falls within a pixel, hey, TypeGPU, someone wrote on chat, yeah. For each pixel, we run the fragment shader. So our goal to run is for everything. We'll start simple with a triangle. So let's get started. We can get rid of the 2D context, and we can already say, hey, let's go with WebGPU context. And also we have to update the type to GPU canvas context, because that's what we're going to be using today. Okay, this is no longer necessary. So in WebGPU, the root of your program, you could call it, that's a little foreshadowing, but you need to ask your physical device to give you like a logical device. So you're going to request via JavaScript access to the underlying GPU, basically. So in TypeGPU, we kind of abstract it away. That's why I called it a root. A root is like the root of your program. You have to create it. You can create it by itself, or you can create it if you have an existing device, you can pass it to it. So we can just do const root equals tgpu.init. Of course, this is asynchronous. So if we look at it, we have a TypeGPU root. And just as I promised, if you want the WebGPU device equals root.device. So this is the GPU device that you can use for the vanilla WebGPU API. You can basically use it normally. So yeah, let's write a shader. Let's start with the vertex shader. So let's do const vertex main equals tgpu. And things that we'll be using today, a lot of them are under the unstable namespace, or an object, you could say it. This is a way for us to tell you that we have a working implementation and we like it, but maybe you want to wait a bit of time to gather some feedback and to test it out in like non-obvious use cases. So if you see something in the unstable namespace, it does not mean that it doesn't work. It should work most of the time, but maybe we are not quite sure that that's the API everyone's going to want, so we are open to changing it. And if we decide to change it, there will be no deprecation. It will just go away. That's for us to like rapidly develop, basically, and not have to worry about changing the API often, since TypeGPU is very much an ongoing project. Okay, so let's do a vertex fn. This is how we tell TypeGPU, hey, from now on we'll be writing a vertex function. We need to tell the vertex function what it expects as input and output, and we'll do it in this structure way. So what does vertex fn take in? So when we are going over our program and trying to output the locations, we have to know which vertex am I in. Yeah. So because we start in the lower left corner. So this is the first. So I have a list of points in space, and I have to know, yeah, it's time to output the first one. And then in the second iteration, we have to output the second one. And there is a nice little thing. We can look at the WebGPU spec. Those are called built-ins. Those are things that you can pass to shaders that are already defined and sometimes necessary to have a working program. And we're going to be utilizing them today. So this one is called the vertex index. So we can just ask kindly a WebGPU to give us a vertex index, and we can then use it inside our shader code. So let's do that. Every WebGPU or WXL data type is reflected in TypeGPU. We can just I will import it as a namespace for my convenience from TypeGPU data. Okay, so this little thing contains all of the data types that we will need to write shader code and to define any structures we might need along the way. So if we take a look, we have the built-in, and if we look here, we have listed basically the same built-ins that are available in the spec. So that's how we're going to tell our vertex program, hey, that's what we are using today. I'm going to call it, let's say, VIDs for vertex ID. And we are going to define it as a built-in that is vertex index. Okay, so now we know that when we write our callback, we will accept one argument. This is going to be the index. And what are we going to output? Well, we have to output two things. One thing is the position. So we already discovered that the device coordinates, which is basically what the position is, specifies for this vertex, where am I in this space? So we have to output a value that falls within the x minus 1, 1, y minus 1, 1, and z is between 0 and 1. Everything outside of this space will be just ignored. So this is one of our outputs. So we'll do pos. It's built-in position. Actually, we can also check it with the spec, but you have to trust me on this one because I won't be fact-checking everything as I go. And also, because we want to draw an image, we have to pass something that the fragment shader, which is the shader that will receive the positions along with anything we want, basically, with some limitations. We also need to know where in the picture are we. So there's also the texture coordinates, which are called UVs very often. And this is another thing we have to return from the program to let the fragment shader know, hey, where in the texture do you expect me to be? So if we pass one vertex 0 and 1 and one vertex 1 and 0, every point along the way will be interpolated somewhere between those two values, which will help us properly draw things. So we'll also have to specify the UV. There is no built-in for UV, but we can just do two-component floating point vectors, which is called vec2f. We won't call it. So this is the schema. Okay, so we have working, let's call it a shell of an implementation. Now it's time to actually define what we are going to do. So we can call this and provide a callback. As I specified in the input, we have a VID, so TypeScript knows that we are expecting a VID, and we are going to return, okay, and we are going to return something that resembles the output we specified. So for now, let's just return default values. Let's do for position vec for f. Then you can see I'm using vec2f here, just using it as an object, and also I'm calling it. The difference is one specifies a schema, so we are telling we don't want a particular value, an instance of this data type, but we want to use it as like a structural type. So we expect a vec2f. We are not using a vec2f value. When I call a schema, like here, I am telling you, hey, I'm an instance. I want an instance type. So we'll get a vector for f as a value, not as a schema, basically. Okay, so let's also return a UV to f, which should be a proper signature. Yeah, TypeScript is happy, but of course our program does nothing at the moment, which is not very good. Let me just get my formatter working again. Okay. Okay, so we have our shell ready. Now it's time to actually define the vertices. So let's go back to our reference. And as we established, we want to draw the first triangle. So the order of the vertices in this particular case does not matter at all, but we have to be consistent. So let's, for now, assume that we're going to lower left, upper right. This is going to be our order, so let's check with the spec. The coordinates are -1, -1, then we'll do -1, 1, and then we'll do 1, 1. Oh, thank you. Someone pointed out that formatter failed because I can't write. Yeah, thank you very much. Now it should work. Okay, so let's go ahead and define those vertices. So let's do const positions. And mind you, at this point, we are writing a shader. We don't have to know it necessarily, but everything inside this function, along with the header, will be used to create valid WebGPU code, more specifically Wixel code. And we can take a look at how the generated code looks later. But for all we know, we are writing TypeScript, and it's going to work on the GPU. So let's start. We have -1 and 1 is our first vector, so we'll do the vec2f. -1, -1. Okay. The second one was -1 and 1, so we'll just copy over the first part. Okay, -1 and 1. And the third is going to be 1 and 1. So we just define a triangle in this space that we are supposed to. Now we also need the UVs. So const UV. And we also have to be consistent, so let's check with the spec again. Going from the lower left corner, we have 0 and 1 is the first coordinate. We'll do vec2fs. To f. Copilot is trying to coerce me into accepting his answer. I will not be doing that. He's a saboteur. Okay, the second point is 0 and 0. When you're creating vectors in TypeGPU, there are shorthands. So basically, if you write vec2f00, it's exactly the same as passing just one argument. This will create a vector regardless of the size. Every component will be what you passed. And if you pass nothing at all, it will be all 0 initialized. So, but for the let's stick to being verbose for now. So there are no, so it's not confusing. 1, 0. Okay. So we have defined our first triangle. Great. Now let's return it. So UV, we can just pass it since the name. UV is, this is UVs, not UV. And we have to actually index into it. So UVs at VID. Okay, so this will, depending on what vertex index we are in, will pick the appropriate UV. We also have to do the same for positions. So we do positions of VID. And as I expected, we have a type error. The problem is we are returning v2f, which is like the instance type of vector. So we are returning a 2-component vector where position expects 4-component vector. As you can see, it's a type error, which is great if you've ever worked with shaders before that are just strings. So we have to adapt. So we'll do vec for f, pass in the position, then 0 and 1. And okay, the signature is happy. We should have a working vertex shader. Of course, no way to test it yet, but as we all know, it's time for the fragment shader. So the shader that will receive the positions and the UVs and will return something. For now, we'll make it like return a solid color. So let's do const fragment main equals TGPU unstable. This is, of course, also unstable. And fragment fn. The structure is very similar. We have to define what the entry point. Entry point is like you know what the entry point is. It's like a point where the program enters. So entry point for a shader is either a vertex function or a compute function. Those will be like the starting point of your program. Okay, so let's do in. What are we expecting as input? Well, our vertex function outputs position and UV, but since a position is a built-in, it will be implicitly consumed by the fragment, so we don't have to take care of it. We just have to take care of what we've defined, so we just take the UV. So let's make it match. If we didn't make it match, later the program TypeGPU would statically check that we are creating an appropriate combination of vertex and fragment and would probably tell us that we are doing something bad, but let's not check it right now. And output of our fragment main will just be a color. A color will be represented as a 4-component vector for the, as you probably know, red, green, and blue channels, along with alpha. We will not be playing with alpha today. We'll just keep it always as 1, but we have to adhere to the rules. So let's do vec for f. Of course, we have the schema, not the instance type. Okay, so now it's time for the implementation. We will take the UV. And for each UV, let's for now return just a vector. Vector for f, let's make it red. Okay, so we're setting red to 1, green and blue to 0, and alpha to 1. It won't matter for now. Okay, now that we have a vertex and fragment pair, we can create a pipeline. Pipeline is basically a combination of those functions that we can call. So we create our little program, which consists of vertex and fragment. We create an object that we can pass additional resources along with commands, and we'll execute them for us. And the result will be displayed however we want. There's really a lot of freedom when it comes to shaders. What we are doing today is, I think, one of the most basic use cases, but it's still awesome. And it's pretty simple. So let's try creating a render pipeline. Pipeline equals root, unstable, with a vertex. So this expects a vertex function So we'll pass vertex main along with attributes. We don't have the time to get into what attributes are. All you have to know is we don't have any for now. And then we have with fragment, and we pass the fragment entry point. But as we'll see, with fragment expects also targets. So as the fragment function returns a color, but it doesn't necessarily know what kind of format we are expecting. So we'll have to tell it that the target format is something. And the most, let's say the most basic and the most widely accessible format is called RGBA 8 unorm. What this means is that for each color we'll have a byte that is represented as an unsigned normalized. So a value between 0 and 255 that will be normalized to 0 and 1 at the shader execution time. So basically, number between 0 and 1 with low precision is what you need to get from that. Let's format it maybe in a more friendly way. Okay, and we can do create pipeline. So this is a working pipeline. Now we'll need to execute it. First of all, we need to configure our context because we haven't done that yet. The context needs just two things to be configured. It needs to be associated with a WebGPU device. So we need to tell the context, hey, this is the device you are going to be working with. And second of all, we need to pass the format. We could choose the format. I think there are only two accessible, but you can also check which format your current device prefers and use that. And we'll do that. So we can do const preferred format equals navigator, which is a widely accessible object, GPU, and get preferred canvas format. So this will output, I'm pretty sure, either the format I specified earlier, so RGBA 8 unorm, or the reverse, so BGRA. We don't have to worry about that. It will all be converted under the hood for us. We don't have to worry about that. We'll just configure it with the preferred format because that could possibly prevent some conversions and make the shader run a little faster. Which even if we did it the slower way, it's just fine. The shader is not very expensive. But let's configure the context now. Oh, I just noticed I misspelled it. Context. I will probably misspell many things today. You have to forgive me. No const. Context. Configure. So just as I said, we need to pass a device. We can get the device from our root. So this is the actual logical representation of our physical device. Let's call it that. And a format, which we just fetched from the Navigator API. Okay, so the context is configured. Now it's time to try and draw something. So let's take our pipeline. We specified at the pipeline creation time what format we are expecting, but we didn't actually tell the fragment function where are you storing the data. It doesn't know what to do with it. That's what we need to do at pipeline with pipeline when we call it. So we have to do with color attachment. So we have to attach a place where we'll dump our color, which in our case is the context of the canvas. So let's call that, and it accepts a view. View basically is a sub-resource of a texture. So if you have a texture, you can think of view as some part or maybe even the entire texture. So let's do context, get current texture, and create view. So if you call create view with no parameter, it will just give you the entire texture, which is exactly what we want in this case because we want to use the entire canvas. I paid for the entire canvas, so I will use it. Next, we have to handle two things. First, there may be something already in the texture when we start to consume it. So we have to define what a load op is. Load operation basically means, hey, if there is something there, what do I do with it? We have just two options. We can either clear or load. Since we don't expect anything important to be in the canvas each frame, we can just clear it. And we have to decide store op. So when I finish calculating my color, do I actually store it in the texture or do I just discard it and use it for something else? This is kind of, I would call it pretty advanced usage. So we just store it and tell it just display it. We don't care about anything else. And each time we call the pipeline, it will take the context. Okay, I will clear it and I will store whatever I created up until the next frame. Great. So we have configured our pipeline with the color attachment. So now we can draw. We pass it the amount of vertices, and by default, every 3 vertices will be converted into a triangle. So our 3 vertices should be properly processed into a triangle, and the fragment shader should be called for each one of the pixels that falls within the triangle. So let's just draw 3 vertices and see if it works. Okay, let's inspect, so we'll see any errors. Okay. Oh, that's curious. We have incompatible formats. Oh, yeah, that's because I hard-coded the format, and we actually have it here. So, yes. We actually have to, we specified a format that we expect, the fragment expects will be drawn into, and then we just said, no, it will be this one. So this was an error on my part. Now it should work. Yeah, okay. We have a working example. So as you can see, this is the exact triangle we wanted to draw. So we have successfully drawn one triangle, which is a big step, I would say. So let's do something more interesting before we move on. So let's try and use the UV values. So as we said, the UV, as we can see in the spec with which we used, we just passed the value 0, 1, 0, 0, and 1, 0. So for every point in this triangle, if we pass the UV as the R and the G channels in the for the color, it should produce a nice gradient from green to red. And black, of course, because at 0, 0 we have no color. So let's do that. We can just pass the UV. And let's see what it produces. And just as we expected, we have a nice gradient. And it should work as we expect, because if you look at the spec, which we just used, there is U of 1 and V of 0, which means that we use the first component of U as red, and it, as we can see, this is just red. And analogously, the green channel is filled here, but no red, and everything in between is done. Okay, we have a nice gradient. Let's add a second triangle, so we actually have a square drawn on the screen. We'll follow the exact same pattern. So we have drawn this triangle. Now let's arbitrarily choose that we will start in the lower left corner, go up and right, down, and to the left. This is not the easiest and most optimal way to draw this square, but I think it will do just fine for today. Okay, so let's go -1, -1. So we'll just copy the first position since we start in the same point. And when we reach vertex index 3, so 0, 1, 2, 3, we'll know we started another triangle. The program will know, so we'll just use the next 3 positions to form the next triangle. So the second one is 1, 1. Oh, okay, 1, 1. We could use shorthands, but let's make it as clear as possible. And actually we have to do some big thinking here, because they didn't tell me what this is. So this is x minus x1 and y minus 1. Okay, these are our positions. So now let's also fill the UVs. So we'll start at 0, 1, the same point as before. Okay, the second one is 1, 0. And the third one is 1, 1, which I should already know, but never hurts to make sure. Okay, so now we have defined 2 statically placed triangles in our vertex shader. Let's draw 2 triangles. So we need to say, hey, now we have 6 vertices. So take the first 3 and form a triangle. Then take the second 3 and also form a triangle. Let's see if it works. And it does. We have a nice gradient, exactly as we expected. Great, but a gradient is not necessarily what I promised you. So let's maybe start going towards our goal of doing liquid glass. So the first thing we want to do is load an image. It will look pretty similar, but we have to understand how a shader consumes resources. So the GPU has its own resources. We can tell it via JavaScript to allocate them, and we can also dispatch commands to write to those resources. But the GPU program, like the vertex shader or the fragment shader or anything in between, will need to use the GPU resources. We can only write to them via JavaScript, and we can use JavaScript values sometimes inside those shaders, but they won't update between dispatches. They will just be used like statically in the generated string code. So we need to pass the texture. We need to somehow get our image bitmap that we received from the create image bitmap API and pass it to the shader in a way that it can read it. So there are two main ways for a GPU to access data. There are buffers and there are textures. They are pretty similar in most ways. I like to think of it as buffers are mainly used for like serial access. So when we can do like arrays or just a single value or like a single floating point number, you can pass via buffer, or we can do arrays, or we can do arrays of arrays. It's really up to us. So we can do basically anything as long as it follows like a pretty loose set of rules. But I like to think of it as the linear access pattern. So we are going to index into, this is not exactly what we want, because we are dealing with an image, which is a 2D data structure. So we could model it via a buffer. There is no problem for it, but it's most convenient to do it via texture, which is like a specific thing it's supposed to do. And apart from being able to store the data two-dimensionally, it also has some nice hardware-based utilities that let us sample at any point, regardless if it's like within the discrete value, because we have to specify the size for the texture. Let's say it's 64 by 64, but we are sampling it in a normalized space. So we are sampling not between 0 and 64. We don't pick one number and sample in this place, but we tell it sample between 0 and 1, and wherever it falls, just give me the best value you can. You can define, there are two main strategies. You can either do linear, so if we just assume a grid, like let's say we have 2 by 2 pixel, 2 by 2 texture, for simplicity's sake. And let's say we sampled at point 0.4, 0.4, so somewhere here. We could just load this pixel, so take the closest one. This is what's called nearest sampling. But the textures also have the privilege of giving us linear sampling. So choosing this point will interpolate nicely between the 4 surrounding pixels that will provide us with smooth values, which is great. And this is exactly what we want at one of the biggest advantages of textures. So we have to create a texture. Well, it's not that difficult because, as you will notice soon, we have already done it, basically. Because what is a canvas? It's a texture, especially the WebGPU context. We configured a texture. So we passed it a format, and we passed it a device. When we are creating a texture with TypeGPU, we basically pass the same things. Apart, we have to tell it what size it is, because context knew what size it was, because we know the size of the canvas at runtime. But we don't know, we can specify whatever size for the texture, so we need to pass it. So let's do it now. Let's say image texture equals root.unstable.create texture. Okay, and it accepts an object that's the descriptor. So let's do size. We can specify any size you want. We'll take advantage of the fact that we already have everything we need. And so we'll do just image data width and height. So we'll create a texture that is the same size as the picture we loaded. We could pick arbitrary size, and TypeGPU, when loading the image, as I will show you in a second, will resample it so it actually fits properly and is not stretched or cut or some runtime errors. But we'll just, for simplicity, do the image width and height. And format. We will just do RGBA ATU norm. It allows nearly all usages, so we can be pretty sure that it will work on all devices that support WebGPU, which is more and more. Okay, image texture. Now let's use the TypeGPU API and just call write. What does write accept? Well, it accepts either an external image source or an array of external image sources in case we have like a 3D texture, not a 3D texture necessarily, but maybe a texture that has multiple layers. We have just one layer, so we'll pass the image data. Okay, looks like it's done, but I expect a runtime error, and we will see it. Yeah, destination texture needs to have copy destination and render attachment usage. We didn't specify those. Every TypeGPU resource comes with the copy flags, copy destination, copy source by default, but we didn't specify the usage as render attachment. So we have to do it now. We just call usage and render. Okay, let's try and run it. No errors, everything is okay. So in theory, we should have image texture should have now inside of it the picture. Now we just have to display it, which is the trickier part maybe. So when it comes to buffers, you can just kind of use them. So you can think of them as the data they contain. So if you have a structure that contains an array, you just index into it and you have the value. But with textures, because of the specifics and how we can do sampling that is maybe linear, we have to use something that's called like a texture sample. So there are some standard functions that WebGPU provides that we can use to access textures. So let's look at that. We have a lot of those here. Texture dimensions, texture load, and so on. We are interested most in texture sample and texture sample level. I will explain the difference between them when the time comes. So we can take a look at the signature. It expects a texture, a sampler, and the coordinates. Pretty straightforward. But how do we do it in TypeGPU? Well, TypeGPU also exports something that is called you export all of the functions under the std namespace. TypeGPU /std. Okay? So if we take a look inside, we can see that we have all of the, maybe not all, but most of the functions implemented. Some of them even work on the JavaScript side. So for example, if you call log2 on the CPU, it will actually give you a value, which is nice for debugging and experimenting with those functions. They should give the same results most of the time because, you know, JavaScript does not necessarily represent numbers as float 32s, so we have to do some workarounds. But for now, let's focus on the texture functions. So we can see, yeah, there are all the texture functions. So let's go over to our shader, specifically the fragment shader. So we now have a point in space that is normalized between 0 and 1 in 2 dimensions, and we want to load the image. So let's do const image data equals std.texture load. Okay, and we need those things that we just discovered in the spec. We are just looking at the first overload, which is for texture 1D, which we are not which is not the thing we want, but we know what the signatures are because they follow the spec. So we know that we need to pass the texture into the shader. We have to tell the shader, hey, this is the resource, use it, generate the correct code. TypeGPU does a lot of this under the hood for us, so we don't have to worry too much. We just have to use views, which I described, which is a sub-resource of a texture. So let's create a view, const image sampled, which will be a sampled view of the texture. So image texture, create view, which is, as you can see, very similar to the way we just used the context texture, because, as I said, they are basically the same thing. But we can see a TypeScript error. Texture not usable as sampled, call usage sample first. So this is one of the niceties when using TypeGPU. This is now a type error, not a runtime error like we had in render. We strive to get as many of those errors to be static as we can. So let's do what it says. We say sampled. Okay, we have a sampled texture view. So now we can go to our shader and pass it as the first argument. When you pass resources to TypeGPU that are from the JS side, so when you have the, let's say, a pointer, which is not exactly correct, a pointer to the texture view, you have to say, okay, use $, to specify we are using its value here in the shader, and TypeGPU will do all the resource binding, all the translation you need. So we also need a sampler. This is pretty simple, so we just create it, const sampler equals tgpu unstable create sampler. Whoa, not TypeGPU, I'm sorry, root unstable create sampler, and we pass an object. We'll not be going into detail what max filter and min filter mean. We just see that they are linear and nearest. Linear means the linear interpolation I described, so it will try its best to interpolate between values to give the best possible value, and nearest will just do the closest pixel to the coordinate you provide. We'll do linear because we want our picture to be smooth. Min filter, also linear. Okay? And similarly, we can just take the sampler, access the $, property, and we just told TypeGPU all it needs to know. Now, all we need is the UV. And it should work. And it doesn't, because, let's see the error. Image texture, it has the image sampled. No, it should work. Okay, let's try to restarting the language server. Maybe something went wrong here. No. Texture load, image sampled that $. This should be correct. We have a sampler. What did I miss? Oh, it's texture load, not texture sample. Well, I'm just blind. Okay. Okay, now it works. Great. So instead of returning our pretty gradient, we can do image data. And let's hope, yeah, we have the image that was automatically adjusted to the size of the canvas. Yay. We got I think, the most difficult part out of the way. We have a working shader, and we are displaying image using it. Now it's going to, I think, be easier from here. Okay, so we have a working shader. Let's try and draw a rectangle. So we need the shape that we'll later use to do the liquid glass effect. So we have something in one of our helper libraries called TypeGPU SDF, which stands for Signed Distance Field, which is a very powerful and useful way to describe shapes in continuous space. So let's do SD rounded box 2D, which we're interested in, and let's just see what it does. So let's go into our fragment shader and say, for the given UV coordinate, get me the distance to the rounded box. So we'll code the function. Let's see what it wants for us. It wants the P, so which is the point in space, which we'll just use as UV. It wants the size. Let's do, like, for now statically, let's say that it should be like a square with 0.2, like 20% width and height. And also wants a corner radius. Let's make up some value for now. Okay, so we have for a given UV point, we have a distance to a rounded rectangle that is at 0, 0 with the width and height 0.2. So what can we do with this distance? Well, since we are going to explore every point in this little space, we can do conditionally. Maybe let's do the conditional after the sampling. If the distance is smaller than, let's say, some threshold, so we are very close to the rectangle, or at least this close to the rectangle, let's return the red. Can it? Oh, thank you, Copilot. So we can return just red if we are close to the rounded rectangle. Let's see. Okay, so as you can see, we have defined a function that places a rectangle at 0, 0 with a radius 0 to 0, 2, and if we are close enough, paints the pixel red, which is a great starting point, but that's not necessarily the best place for us to place the rectangle, since it's just a white background. So let's create a helper function. TypeGPU lets you write normal JavaScript callbacks with a little caveat, which we'll get into, that you can use in your shader functions. So let's do that right now. So let's do our own rounded box that is not placed at 0, 0, but at 0, 5, 0, 5, so right in the middle. Let's call it my rounded box. And it's going to be a callback that accepts the same arguments as this function, so we'll just copy it. Yes, okay. And it will return this function, so return as the rounded box, and we'll just pass the parameters since they are compatible. And we can replace this with this now. But since we are doing some transpiling, we take the TypeScript and we don't run it on the GPU since it's not really possible. We transpile it to the Wexel language, which specification we were looking at previously. We have to signal to our plugin, hey, this function is going to be run on the GPU. Yes, so let's try and run it as it is now. As you can see, the resolution error, function myRoundedBox is not marked with the use GPU directive. So we have to go to the function and say, dear transpiler, this is GPU. This is going to be run on the GPU. If you do the directive, we can see this is just an identity function. So yeah, we've done it. We've done a JavaScript callback that we can call from a shader, which is, I think, awesome. And while we're at it, at any point, TypeGPU lets you see what it generates. So if you want to see how our current shader looks as it's executed, we can just do console log, take the pipeline, TGPU.resolve, and we pass as externals the pipeline. Okay, and if you console log that, we can see that we get the entire shader. It's pretty pretty small. The font is pretty small, but I hope you will get the point. It's not really important to parse the shader too good. You can see we have everything. We have the vertex main function. We have the SD rounded box, which is actually code that we used from the TypeGPU SDF library. And we have the myRoundedBox function on top of it. And everything, every group binding, you never have to worry about that. Let's not say never. You sometimes don't have to worry about that if your program is simple enough. But you never have to worry about manual binding, choosing the group and the binding specifically. You can do that still if you want, but why would you? And we have our fragment function. This actually is the code that is sent to the GPU, one-to-one. So it's nice that we can, at all points, inspect. It's nice for debugging, and it's pretty accessible, I think. OK, so now that we've done that, we inspected the code. Let's actually make our myRoundedBox function do something. So since we want the rectangle to be at the middle, it's as simple for us as calling sub, which is basically vector subtraction, but JavaScript does not have support operator overloading, which should be boycotted. But we have to write 0.5, which basically is the same as doing p minus d back to f 0.5. This is the result is the same. This would actually work, but TypeScript would be angry because it doesn't understand operator overloading, but we will transpile it correctly. So as long as you're fine with type errors, which you shouldn't be, this also will work. But we'll use the proper TypeGPU way. And let's take a look. OK, we have the rounded rectangle in the middle, which is a great step in the right direction. But as you probably noticed, I tend to refresh the page very much, and we have to do it every time, since we are calling the pipeline once. So we are telling the program once at the start, do all the work, draw the image, and then do nothing. But if you want some reactivity, so if you want to change something inside the shader via a buffer or a texture, we need to draw it again. A common way to do that is to just draw every frame. And there is a nice API on the web for it. It's called request animation frame, which will actually run the callback inside at your screen refresh rate. So let's maybe use that so that we render every frame, not just once. So let's call it frame. And all it will do is just call the pipeline. And at the end, request animation frame with itself. So we just pass itself. And we have like an infinite loop, basically, that will draw every refresh. OK? So now we should have a more reactive simulation. OK, everything is ready. Now let's do something more interesting. So we have the distance, but we are not really interested in doing the liquid glass effect on the entire thing, because what I imagine it as, let's draw it out, is we have a hard surface, which is basically our image. So this is the little prompts we are writing on. And we have the surface of the water, or some liquid that is dense enough to cause a refraction of the light. So that's a terrible drawing. I hope you will forgive me. But I think it's clear enough. So our current approach is that we just sample this point, sample every point directly where it is. But now we can use the fact that we know where the edge of the rectangle is. We can define it and do some special behavior there. So if you want to do liquid glass, we should loosely model how physics work. We won't be doing a Snell's law or anything like physics related. We'll be doing a simplified one, but I think it's good enough for today. So basically, light will curve, and instead of sampling directly beneath it, it will sample depending on the curvature of the surface. So if we go like this, so this will be a little more curved. We have to model that. Oh, I'm sorry if I'm speaking too fast, but I'm really running out of time, and there's a lot of interesting things I want to do. Thank you for your comment. Someone said I'm at 2x speed, which is probably true. OK, but I will not be slowing down. So let's try to establish the outline. So we are just not interested in this part because, as we said before, this is just our normal behavior. If our ray lands here, we just sample directly beneath it. We're only interested in the edge. Thank you. Eva said people usually put videos on 2x speed, so we are doing them a favor. Thank you. I'm trying. And let's establish distance equal greater than 0. So the thing is, signed distance fields are basically just amazing. So for each point in space, we get a distance to the shape, but it's the key part is signed distance field. So if you are outside of the shape, the distance will be positive, and if you are inside the shape, let's say in the same distance, the distances will be the same, but the sign will be inverted. So we can use that to our advantage and create like the outline. So we are going to check if we are within a distance, but greater than 0. So we are not inside the circle, but a certain distance outside from it, which I just done. So let's see if it works. We should say, yeah, we have a nice frame that we're going to use for our further calculations. We should make it a little bigger. For now, it's a hard-coded value, which we can totally live with. Okay, so this looks pretty good. This is the area where we'll be curving light. So let's try and do that. This is pretty straightforward because we actually already have all that we need. The distance from the shape is actually how much we want to curve the light. Because if you think at it, the further we are from the shape, but still within it, the more the curvature is. So we can use the distance, for example, square it, and this will make it so the further you get, the more the curvature affects it. So let's try and do that. Instead of returning a solid color, we will try. We will calculate an offset. But okay, we'll calculate an offset, but we don't know which direction to offset. So just to illustrate it, so it's very clear. If we can tell what's the distance, but if we are in this place currently, we only know the distance, but we don't know the direction. So we know how much to offset the light, but we're not pretty sure in 2 dimensions where to do that. Well, the amazing thing is we can estimate that pretty easily. Because if you think about it, if we take this point, sample a little beneath it, a little above it, to the left and to the right, we'll actually get a gradient that describes how if we're moving away from the shape, are we moving towards the shape, it will provide us with a nice vector that will tell us the direction. So let's maybe try and do that pretty fast. It's as simple as defining like a constant distance. You could make it more elaborate, but in the interest of time, I will be just doing 1/1024. For no particular reason, you could experiment with it. I'm pretty sure SDFs are amazing. Yes, they are. I'm pretty sure most values that are within some reason will work here. So let's do const. We'll call it, naming variables is truly the hardest thing ever. So let's call it the x. Let's call it, okay, I will stick with dxp, which stands for in the x difference in the x-axis positive, which is a mouthful, but we'll stick with that. We'll take my rounded box and sample it with the exactly same parameters. Apart from here, we're going to add to the UV. So now we are going to do in the x-axis positive. So now we are doing this little point. So we're moving in the x-axis to the right side. Let's do that. So let's take our UV and add to it in the x-axis epsilon, and in the y-axis nothing at all. We need to do the vec2f, so it's 2-component vector. Okay. Okay, so we have our difference in the positive direction. So to do negative, we'll just do subtraction. So we just landed on the other side. So right here. Okay, so we have one of our vectors. So the change is how our distance changes in the x-axis. Now we're going to do exactly the same thing, but in the y-axis. So we are instead of adding epsilon here, we just zero it out and add and subtract epsilon in this direction. So basically what we have now are 4 samples. Now we have to do a vector based on them. So let's do const, let's call it direction. Okay, this is not what we want. As I say, Copilot is the biggest saboteur of them all. Okay, so we are taking our vector in the positive and subtracting negative. So if you want to illustrate it, we are taking this vector, or this, math is hard. Let's assume we are taking this vector and this vector, and we are combining them to have some sort of like something like this. Possibly, if we had like a big change in the x-axis, we'll have a vector like this, and a small in the y, we have something like this. now we can combine those vectors and just take the direction. So we don't care about how much it changed. We just care about the direction. And there's a lovely function called normalize that will just take the direction part of our vector. So we'll do std normalize. Okay. And we have a direction. Okay, now we have all we need. We have how far away are we on the shape? We have the direction. Let's sample. Yes, because we have to sample the image again in a different place. So let's do const offset, which will be just the direction multiplied. So we call mul by the distance. This will not look too good, I reckon, because it's just linear. But let's see how it looks for now. So we'll see new sample equals std texture sample uv, and to the point uv where we are sampling, we are going to add or subtract. We'll figure it out. I think subtract is the right thing to do. Offset. But if you do add instead of subtract, you will get just another interesting effect. It depends on what that's why shaders are amazing. Sometimes the mistakes are actually what creates the most visually interesting effects. So we have the new sample, but there's a problem, and you will see it. If we return the new sample, we will run into another runtime error, because there are some restrictions to how we can use sampling, because it's called a collaborative operation. So it's not done by one thread at once, but it's done in a group of threads, and they each collaborate to, for example, figure out which mipmap level. I know these are, for some people, magic words, but I think it's interesting. If you are feel free to research that. But all we need to know is there is another method called texture sample level that does not require collaboration across threads, but requires us to specify which mipmap level. Again, I will want to go into mipmapping right now. Which mipmap level we want to sample. For us, it's 0 because that's all we have. So this should run now. Yeah, and it does. As you can see, we have the offset. We can pretty easily change how much we offset. For now, it doesn't look amazing because, as I said, you can see the line is straight, which doesn't look very glassy. So let's do something with the distance. Since it's a number, we can just take it to the power of 2. But since it's a very small number, because as we can see, it's between 0 and 0.05, it will look like nothing. Maybe if you have very sharp eyesight, you can see some offset. But let's try and make it a little more noticeable. Okay, so we take the distance, square it. We bring it we kind of normalize it. We kind of normalize it between 0 and 0.5 now, since we multiply by 10. We could do 20 to normalize it between 0 and 1, but from experience, I know that this looks kind of nice. This looks already like a kind of a liquid glassy effect, but it's hard to see when it's static. So now I hope I can be fast with it. I will introduce some interaction, because that's, I think, the most powerful part about shaders on the web. That they bring a lot of interactions to interesting visualizations. So let's create a buffer. I talked about them so much, yet I haven't created one. So let's do it. TypeGPU provides some nice utilities. So we can just do const mouse pose. So now we are defining the data structure that will allow us to send data to the GPU for it to access. And when we update this on the CPU side, it will, I have to be more specific, not to confuse you. We can send commands for the GPU to update this buffer, and it will be reflected in the code. So we can do root that create uniform, which just specifies that this will be uniform, and storage are two ways of creating buffers. Uniforms have more restrictions and have to be smaller, but since we are just passing one 2-component vector, we'll be just fine. So let's do vec2f as a schema, not as an instance type, and do initial value of 0.5, so the middle of the screen. And we have a uniform. What can we do with it? Well, we can just use it, thanks to TypeGPU. Normally, this would be a little more involved, since you need to define the resource layout so the shader knows what it does. We know what you're trying to do, and we're going to do it for you. So let's do mouse pos dot dollar. So the usual pattern for accessing TypeGPU resources on the shader side. And in theory, we should have the exactly same effect. Yeah, for now it's static. So we are sourcing the value not as a hard-coded value, but we are actually reading from a buffer on the GPU side. Now it's time to add some interactivity to it. So we want it to follow the mouse. Well, it's like, really, the web is the perfect playground, since we already have a whole event system set up for us. So all we need to do is go to Canvas, add event listener. We will do mouse move. Mouse move. Yeah. And we'll do the callback. So we take the event. And what we want, because the event from the browser will give us a pixel value. We don't really want that, because as we established, shaders operate on normalized values. So more specifically, the UVs we are operating on are between 0 and 1. So we have to normalize the mouse values to have the proper position sent to the GPU. So we'll get, there are some pretty nice APIs. One of it is we can get a bounding rectangle, bounding rect of the canvas, which will tell us exactly where on screen the canvas is. And now we can calculate const mouse pos equals vec2f. Yeah, thank you, Copilot. He inverted the y-axis for no particular reason. So let's just go over the code to make sure we are all on board. We are taking the client x, so the pixel value of where we are, to subtracting from it the starting point, so where the canvas starts, and dividing by width, which basically tells us between 0 and 1 in the x-axis where is the mouse, and we are doing the same with y. All we need to do now is take our mouse pos buffer, so the did they call it mouse pos uniform? I would assume. No. What did I call it? Oh, no, that was not the best of names. Let's change it. Okay, mouse pos uniform to represent what this is. Okay, and all we need to do on the CPU side is tell it to write the mouse pos value here. It's of course it's checked statically, so we know we are expecting data to be v2f. So if you pass like 12, well, 12 is not a vector, so you'll get a nice static error, which is sick because you have your GPU data validated for you. That's all we needed to do. Let's cross our fingers and check if it works. Yeah. So now we have a interactive liquid glass simulation. There are some very cool effects that you can add to it, like chromatic aberration. You can do some blur in a couple of ways. But unfortunately, that's all I'm going to be showcasing you today. I hope it was like a nice introduction to what is possible and how maybe TypeGPU can help you achieve it. If you want to learn more about shaders, we have an up-and-coming learning platform that we are working on. I will give you a little bit of sneak peek. Let's go to localhost where something interesting awaits us. So we're working on a platform that lets you write shaders just like I did today, but with nice descriptions and interactive. So actually, as you change the code, as you change your TypeScript shaders, which still sounds crazy to me, the output will actually be updated. So even if we have some validation for when the time changes. So that's something we're working on. And if it's not available yet, because there's a lot of work to do, but if you are interested in learning more about it, or when it's ready, you can go to typegpu.com, go to our docs page, and when you in the challenges tab, there is you can sign up to get notified when we are ready with it. We hope it will be a great resource that will help you learn to do cool stuff on the web. Why is food so expensive and how you're coping with it? Well, we got fed well at Software Mansion. Okay, yeah, so that's it. I hope you liked the presentation. Maybe some of you followed along, maybe some of you just listened. That's amazing too. I hope I piqued your interest and what is possible to do and how easily you can do it. And yeah, so that will be all for today. If you need anything, if you want to make your own example, you can go to typegpu.com also. Let me do that. typegpu.com. And you can go to our Discord server. We are very active there. If you want to learn, if you are in the process of learning, there will be a VOD, yes. If you are interested in learning more, and if you are stuck with something, we are very active on our Discord. If you would like to do it in TypeGPU, we're always happy to help you learn the ropes. And yeah, that's it from me. Thank you for listening and maybe following along. I hope it was nice and, well, see you.